Hi again. So I'm going to show you how to calculate the delta H of a reaction using the standards heat of formation. Now these are table values. The equation that you would use to calculate the delta H of a reaction is this. The sum of the heats of formation of the products minus the sum of the heats of formation of reactants. So let's take this equation here. The reaction of benzene with oxygen producing carbon and liquid water. So there's the balanced equation. And so what we want to find is what is the value for the amount of heat that's either gained or released in this process. So the values, like I said, will be table values. There's one that I posted here in Google Classroom, and there's one in the back of the textbook. So here's how you would start. You start out on your product side, and so I would multiply 12 times the heat, the standard heat of formation. That little 0 is just to indicate standard heat of formation of carbon solid. And I would add to that 3 times the standard heat of formation of liquid water. And I would close the bracket, and then I would say minus, and then I would say 2 times the standard heat of formation of benzene plus 3 times the standard heat of formation of oxygen, and close the bracket on this side. Okay, so then you can see here that I took and I multiplied each of the values by the coefficient from the balanced equation. So once again, the coefficients are very important. So now I would just look up these values. They're either in the table or in the chart that I posted. And so when you start looking up your values, your first thing you're going to find is that there is no value for carbon. And so that value there is 0. Because these are formation values, it's the amount of heat released when a substance is formed from its elements in their pure state. Carbon exists, it's not formed, so therefore there is no value. Okay, I'll go on. Do 3 times the value for H2O, which is negative 285.8 kilojoules per mole. And I'll close the parenthesis and subtract 2 times the value for the heat of formation C6, which is positive 49.26 kilojoules per mole. And add to that, again, I have oxygen, which is an elemental substance. It exists, it doesn't form, so there's a 0. So if you ever forget which ones have a heat of formation and which ones don't, if you go to look them up on a table, you won't find them. And so that will clue you in and help you remember that elemental substance don't have a value. So like I always like to do, I'll break it down into little algebraic steps. And so I'll take negative 285.8 and I'll multiply it by 3, and I'll get negative 857.4 kilojoules per mole. And I will subtract from that 49.26 times 2, which would be a positive value of 98.52. And because that's 0, I don't worry about that. And so then I'll take this and I'll say plus a negative. And so I'm now going to take 857.4 and add 98.52 but both of those are negative, so the value comes out to negative 955.92 kilojoules per mole. Okay, so that's it. That's all you have to do to come up with your answer. And then if you were to rewrite your thermochemical equation and include the energy term, it would look like this. 2C6H6 liquid plus 3O2 gas goes to 12 carbon solid plus 3H2O liquid plus 955.92 kilojoules. So this is important to know. If it's showing as delta H, I would want to show it as a negative. If I'm showing it within the equation, I would include it on the product side. If I were to include it for an endothermic reaction, then the energy term would be on the opposite side. I hope that helps.